everyone, let's work on an optimization problem now that's sort of like the three-dimensional version of the fitting a rectangle under a curve. So in this one, we're going to imagine that we have a hemisphere with a radius of 1, and within that hemisphere, we're nesting a cylinder. So the cylinder is going to sit with its base on the bottom of the hemisphere. It's centered exactly in the same spot, so its height can extend up until that circular ring around the top of the cylinder touches the hemisphere. So that's kind of a visual on this. And the one thing we know is that the radius of the hemisphere is 1. We are supposed to find the maximum volume of the cylinder. The size of the hemisphere is fixed. The cylinder can change in here. So for example, if you imagine making the base of the cylinder bigger, it would then have to be shorter to fit inside the hemisphere. That's the balancing act we have. We can make the radius bigger, but then the height gets smaller, or we can make it taller and the radius gets smaller. Okay, so volume of a cylinder, that one is one that we just get for free. We don't have to break this up into pieces or anything. The volume is pi r squared h, where r is the radius and h is the height. Let me erase this yellow one so there's not quite so much clutter for us to look at. Okay. So it's pretty quick to get to a formula. The trick in this one is going to be how do we eliminate that second variable? That's definitely the challenging part. And one piece of advice I have for you is when you're working on these 3D problems, it can be harder to spot things. So imagine taking a cross sections, or you can just imagine like flattening this shape out into the paper instead of my attempts at making it look 3D. What we get is basically that the hemisphere becomes a half circle and the cylinder looks like a rectangle. And then what we know is that the radius is either one of these, the height is here, and then again we know that the radius of the hemisphere is 1. The key to this is going to be rearranging that radius to a spot that it actually helps us relate r and h. So this, for example, is also 1, the height of the half cylinder. The magic place that we can set the radius so that it helps us with the cylinder, I keep wanting to say the wrong shape name, is so that the end of the radius sits on the corner of the cylinder where it would touch the sphere. So that's kind of the key to all of this. So this right here is 1, and what we have is this nice triangle. It's a right triangle, and it has a base of r, a height of h, and a hypotenuse of 1. So we can say r squared plus h squared equals 1. And then you can solve that for either variable. If you're really paying attention, a nice way to do it is to just solve it for r squared. We can say r squared is 1 minus h squared, and then back up in our volume formula, we can just directly replace r squared with 1 minus h squared. If you hate that, note that you can go one step further and say, okay, then r is the square root of 1 minus h squared, technically plus or minus, but we want a positive radius. And then when you plug it back in, you'd get the square root of 1 minus h squared squared, and the root would drop out. So you'd get to the same spot if you don't like my skipping one step in there. So this gives us a fairly nice volume formula as a function of only h. I'm going to distribute the pi h in, so we get pi h minus pi h cubed, and I like it. It's a fairly simple cubic. Note that you could solve for h instead and substitute that in. You'd end up with something a little messier. There'd be a square root, but you should still get to the correct answer. It's just slightly messier with derivatives of square roots in there. Okay, so we've got our formula. We want its maximum. We need to take the derivative with respect to h. So we'll get plain old pi minus 3 pi h squared. And we want to know if that's ever undefined. The answer is no. We also want to know when it equals 0. And to solve that, let's see, I'm going to move the 3 pi h squared over to the other side. We can divide both sides by 3 pi. pi's cancel out, so I end up with 1/3 equals h squared. And then I can take the square root, and it's plus or minus the square root of 1/3. Since 1's a perfect square, we'll go ahead and split that up and say it's 1 over the square root of 3. And once again, we can pick the positive. We're not going to choose a negative height for this thing. So we got a critical value at 1 over the square root of 3. We also need to think about domain for this. And you can think of domain as a first step instead of a last step or a late step if you would like to. We kind of use that as we went, but we'll look at it now. So if we think about the possible heights, the smallest possible height is 0. It's not a good choice, but if h equals 0, the radius expands all the way out to 1, and we're basically just getting that circle on the bottom. So 0 is our minimum. The tallest possible cylinder that you can build has a height of 1 because then it's actually collapsed down and it's just a vertical line right up the middle. So again, it's a bad choice, but it does have some practical meaning. I can explain what that looks like. If we start to get beyond a height of 1, we're in trouble because it doesn't even fit the requirements of this problem where the shape has to fit within the hemisphere. Okay, so just to verify that I actually got a maximum, I'm going to plug 0 into my original volume function. I'm going to plug my critical value, 1 over root 3 in, and I'm going to plug 1, my other endpoint, in. If you look back right here, if I plug 0 in there, I definitely just get back 0. Also, if I plug 1 in there, I get pi minus pi, which is 0. So all I have to do is convince myself that the critical value gives me a positive volume, and I found a maximum. So I get pi times 1 over root 3. I'm just going to write pi over root 3 since I'm short on room. And then I get pi times 1 over root 3 cubed. Pi 1 over root 3 cubed. That's a little tight. You can double check that with a calculator. That should in fact give you a positive value. So that is our maximum. Sorry, I shorted myself on space a little bit. Remember when you're done to go back and check what the question asked for. We wanted the radius and the height. So far I've got that the height should be 1 over the square root of 3. If I want the radius, this would probably be the easiest place to go looking for it. The radius is going to be the square root of 1 minus 1 over root 3 squared. When you square 1 over root 3, you just get 1/3. So it looks like the radius should be the square root of 2/3. So this is the dimensions that will give me the largest possible cylinder. Okay. Hopefully that helped. The two-dimensional thing can be a really good trick. Thanks for watching.